Okay, hello and welcome to recitation number 13. This recitation was supposed to take place the week of Thanksgiving, but of course, since we had break, we couldn't have that recitation. So this is the substitute. Apologies for getting this recitation out so late. There were many factors that went into that, but hey, at least it's happening. So today we're going to be talking about relations and the probabilistic method. These are two crazy topics, so we're going to spend a lot of time on them, just massaging out the details of each one of them, so hopefully you have a very, very strong understanding of what goes into them. They're a bit complex though, so just bear with me. So here we see the properties of relations. I went over these in the last recorded recitation, and they were also covered in the recitation before that, so I'm not going to touch on them too much. Just be very familiar with these. We're actually going to touch on some of these in the next slide, but yes, that's this slide. Okay, so here's where the new stuff comes in. Equivalence relations and equivalence classes. Thus far, we have just been looking at relations, and recall a relation is defined on a set, or rather two sets, but they can be the same set, and a relation is a subset of the cross product. Equivalence relations are a special type of relations. In fact, we say a relation is an equivalence relation if and only if it is reflexive, symmetric, and transitive. A relation must have those three properties for us to call it an equivalence relation. It can have the other properties as well. For example, it could be antisymmetric. However, for something to be an equivalence relation, it must have those three properties. So make sure you're incredibly familiar with those. That means if this is the definition of an equivalence relation, the way you would prove something is an equivalence relation is by showing that it is reflexive, symmetric, and transitive. We will need to know this for one of the problems that we're about to do, so keep that in mind. So with equivalence relations, we have something called equivalence classes. And the notation we use are these brackets with some letter inside of it. In this case, we're using A. That just means A is one of the members of this equivalence class. Subscript R to mean that it's the class over the relation R. And this equivalence class is a set of elements. It is a set of elements of A related by R to A, which is what we're using to describe the class. So in set builder notation, the equivalence class is equal to the set of all x in A such that little a is related to x. Okay, so now we have a definition of a word I don't really like, but I'll touch on that in a moment. We say that if B is an element of this equivalence class, then B is called the representative of the equivalence class. However, just saying representative doesn't really describe a unique element. For example, you can take any element in this equivalence class and call it the representative. So in that case, it's not super special. The reason why we use the word representative is because it's so commonly used, namely when we see this kind of notation. Here we would say like the equivalence class such that A is a representative of it. So now it's really like relating the class to an element. But hey, it's an important thing to know, so know it. Lastly, we get to this bullet point, which is quite good. It's one of those following our equivalent statements that we saw for trees, now for equivalence classes. This says that if we have two elements A and B in A, the following are equivalent. So first being that B is an element of this equivalence class. That implies that the equivalence class with representative A is equivalent to the equivalence class with representative B. Rather, they are the exact same sets. And that implies that the intersection of the two equivalence classes is not equal to the empty set. These are all bidirectional. So 1 implies 2, 2 implies 3, 3 implies 1, blah, blah, blah. We can kind of see why 2 implies 3 because equivalence classes are non-empty collections. So each one of these has some element. So if they're the same set, then their intersection is going to have all the elements in the set, which is not going to be equal to the empty set. However, there are a couple of directions that are kind of interesting to prove. Number one is 1 implies 2, and the other one that's interesting is 3 implies 2. Why don't we prove these really quickly on the board? I'll just go through a sketch of the proof since I don't want to spend too much time on it. So yeah, let's take a look. Okay, so now we're dealing with the precondition that the intersection of these equivalence classes is not empty. That must mean that the equivalence classes are identical to one another. So just for the sake of brevity, we're letting S equal the intersection. Since we know that S is not equal to the empty set, it must contain one element, at least one element. So there exists some element X in S. By definition of intersection, if there's an element X in S, it must appear in both of these sets. So X is in this equivalence class and X is in that equivalence class. So since X is in both of these equivalence classes, when we write out the elements, this is going to contain X and some other elements. B, this equivalence class representative B will have X and some other elements. We just want to show that these two are equal to each other. And what I'll claim is that for every element in this equivalence class, it also appears in B. So once again, we'll be proving a subset relationship. The other direction I'll leave as an exercise. This is not that tricky to do. So we'll consider, again, an arbitrary element. Okay, so we have this. By definition, we know that A is related to A sub I. And we also know that X appears in this equivalence class. So we also know that A is related to X. Now we'll just work a little bit of magic. By symmetry, we know X is related to A. And then we'll use some transitivity with these two to say that X is related to A sub I. This is quite helpful because now we can look at this equivalence class here. So since we know X also appears in this equivalence class, we know B is related to X. Well, if we know that, and we know this, then we can use transitivity. Since B is related to X and X is related to A sub I, by transitivity, B is related to A sub I. What that means is that A sub I is going to be in this equivalence class as well. So we've shown for every single element in this equivalence class, it also appears in this second equivalence class. So we've shown that the equivalence class represented by A is a subset of the equivalence class represented by B. Like I said before, opposite direction is pretty similar. I'll leave it as an exercise. We haven't even gotten into the questions yet. Wow. All right, back to the screen. So here's an example of an equivalence relation is equal to. And we'll say that this is a relation on the set of real numbers. And we can prove that it's an equivalence relation by showing the three properties: reflexivity, symmetry, and transitivity. Reflexivity, pretty easy. We need to show that for all elements of our set, that element is related to itself. And sure enough, for all real numbers, X is equal to itself, so it's related to itself. For symmetry, we want to show for every two elements, X and Y, in our set, if X is related to Y, then Y is related to X. This is pretty simple. If X equals Y, then clearly Y equals X. So if X is related to Y, then Y is related to X. Pretty simple. Transitivity, very similar. If X equals Y and Y equals Z, then that must mean that X equals Z, so therefore we have transitivity as well. Those three properties hold, therefore it's an equivalence relation. Pretty simple. And now we move on to the probabilistic method. This is something that I find incredibly difficult to explain in words, just because the word description of the probabilistic method is so abstract. So a lot of this I'm sort of going to be hand waving, and once we see an actual example, that should hopefully iron some things out. But the idea of the probabilistic method is a proof technique for proving there exists an X such that P of X is true. And it's proving these claims directly without providing that X or that element. For example, we've seen problems like this before. For example, on your midterm, we asked you to prove or disprove that there exists an Eulerian graph with, some amount of vertices and some amount of edges, and those of you who got it correct drew the graph and you were like, boom, done. There exists something. However, sometimes what we want to show exists might be a lot more complicated, and it's really hard to just draw out an example, especially when something is like in terms of n or some variable. So that's where the probabilistic method can come into play. The idea of how this works is we construct a random procedure to generate candidates for this x, meaning what could a possible x look like. Then we will show that the probability of the property that we're looking for, this sort of property dependent on x, if that probability is greater than 0, or if the expectation is true, then we can conclude that there's going to be some x such that p of x is true. Namely, if like the expectation is some amount 2.5 and you show the expectation of x is like 2.5, then you can conclude that there must be some sort of x that has, value at least 2.5. That's sort of just how expectation works. Similar thing with probability. We've shown a non-zero probability of something occurring, which means there must be some instance in which it did occur. Again, super abstract. Hopefully with the example, it'll clear things up. Speaking of examples, let's shift over to the blackboard and do some problems. Okay, so here's the first question. And I'm really, really bummed because I recorded this recitation yesterday, last night. And I had a very, very good explanation, in my opinion, of this problem. But the video, the quality was kind of bad. I didn't think it was good enough to publish, so I'm re-recording it. But now it's like, I don't know if I can replicate that explanation. I'll do my best, though. Define an equivalence relation R on the set 1 through 100 with the restriction that there are exactly 2 equivalence classes. Find an R such that it maximizes the size of the relation, and then show that the size is maximized. I really struggled with this question at first, because there's a lot of things that it's asking us to do. First, we have to define a relation R, and then also ensure that it has the maximum size possible. On top of that, we have the restriction that there are 2 equivalence classes. Because of that, you might be tempted to first provide the R, right? Just explain what R is, and then say that, I found something, and for certain the size is maximized. However, that's kind of tricky to do. First of all, you might be tempted to just come up with some sort of verbal description of R. We saw is equal to is an equivalence relation. So we might try to do something similar for this. However, that'll prove to be quite challenging. Instead, you should remember that an equivalence relation, or rather any relation, R, is a subset of the cross product of our set. So we can define R simply by providing a set of ordered pairs. However, it's probably not best to just start writing out ordered pairs and say that they belong to R. Why? Because we have so many other things to ensure happen. First of all, we have to ensure there are exactly 2 equivalence classes, and then we have to make sure that the size is maximized. So what we can instead do is first operate under the restriction that we have 2 equivalence classes. We don't know what they look like, we don't know the sizes of them. We're just going to say we have 2 equivalence classes. Using that information, we can potentially get some sort of idea of maybe what the sizes of them should look like, such that the cardinality of R is maximized, and then from there go back and define an R. So we just need to get a little bit more tangible stuff of what R could look like, and then define it. So let's do that. Okay, so we're operating under the restriction that we have 2 equivalence classes. We'll denote them X and Y. Before we proceed, something super important that I wish was mentioned in the slides, but I guess we just forgot to include it. And this is what you need to remember. Every element of our set A belongs to exactly 1 equivalence class, not 2. And the reason why not 2, we saw earlier, because if that were to occur, then we would have a non-empty intersection, which means the classes would be identical to one another. And also not in 0 equivalence classes. There must be an equivalence class for every single element, exactly 1. An equivalent way of expressing the above is to say that the equivalence classes of an equivalence relation R on a set A, partition A. Remember, equivalence classes are sets, rather subsets of the set A, but these subsets, these classes, partition A. This is something super important to remember. So with all this, we can kind of make two claims. The first one is that the cardinality of our set A is equal to the sum of the cardinalities of our equivalence classes. This makes sense since they partition the set A. The second one is a little less self-explanatory. Namely, the relation R is equal to the union of the cross product of our two equivalence classes. Why is this true? Why might this be true? Well, let's show one direction. Namely, we can show that R is a subset of the right-hand side. And for this, just consider an arbitrary element of R. Right? Just some ordered pair. Well, this just means that A is related to B. Well, that must mean that A and B are in the same equivalence class, because that is literally what an equivalence class is. So if they're both in the same equivalence class, they must either both be in X or both be in Y. Regardless, if they're both in one of these two, therefore the pair A comma B will appear in the cross product. So honestly, that's it for proving the one direction. The other direction is pretty similar, but I'll leave that to you. Actually, I'll just briefly explain it. We can take an element from the right-hand side. It must be in this or that. Regardless, we just use the definition of an equivalence class to mean that, like, if we have a pair in X cross X, then it's in the equivalence class X, which means they're related to one another. Therefore, it's going to be in the left-hand side because that's the relation we're looking at. So that's a kind of brief sketch as to why these two sets are equal. We've shown subsets in both directions, therefore equality. So we'll use this to our advantage. Well, what we'll note is that since X and Y are disjoint, because they partition A, let me just write that down. Since X and Y are disjoint, then X cross X and Y cross Y are also disjoint. You should take some time to prove that to yourself. This makes expressing the cardinality of R in terms of these equivalence classes a lot easier. The cardinality of R is just going to be the cardinality of these cross products summed together since they're disjoint. And if you remember the cardinality of a cross product, if they're both the same sets, it's just going to be equal to the cardinality of the first set times the cardinality of the second set. In this case, they're the same set. So in this one will become X squared and this one will be Y squared. Well, why are we doing all this? We're under the constraint that X and Y are going to be our two equivalence classes. By the way, I switched to uppercase X just because I didn't want to confuse it with the cross product. And I see that I use lowercase y here and capital Y here. Let me just change that. So we're looking at these two equivalence classes. We know that they partition the set A. We don't know what these equivalence classes are. We don't know how large they are. We don't know what elements are in them. But we know that they partition A. So if we just say that the cardinality of X is equal to some value, say, maybe I shouldn't use lowercase x. Let's use, what's a letter I like today? I'm feeling like Q. I'm always a big Q guy. Then the cardinality of Y is going to be 100 minus Q. Because, again, they partition A. So now we're in really, really good shape, right? We're expressing the cardinality of a relation in terms of a single variable. And our goal is to maximize this cardinality. That's what we're looking for. So we're going to find some value of Q that maximizes R. So let's do that. So our goal was to find a Q that maximizes the cardinality of R. We've written the cardinality of R in terms of Q. And this is not an algebra class, so I'm not going to go over all of this, but just expand things out. And then I decided to complete the square, which something I haven't done since like 6th grade. So we do that, do some factorization, and the whole reason for this is we're trying to maximize R, but we need to choose a value of Q that does that. So to maximize this right-hand side, we can sort of ignore this term, since that's going to be a constant addition, and instead we want to maximize this first term. So we can just look at the squared part of it. To maximize a square, we either need to maximize the inner part, make it a very large positive number, or minimize it, make it a very small negative number. But a good question is, what are our choices for Q? Right? I could choose Q equals 10 billion here, and I have a really massive value for R. But is Q equal to 10 billion a viable possibility? Well, that comes down to what Q means here. Q is the cardinality of our equivalence class. And remember, an equivalence class is going to be a subset of our set that we looked at originally. So we know that Q is going to be at most 100. But we can do a little bit better than saying greater than or less than or equal to 100. We can say that it's strictly less than 100. Why? If Q was equal to 100, then the cardinality of Y would be 0, but we do not allow for empty equivalence classes. So Q is less than 100. Again, it can also not be empty, so Q cannot be equal to 0, but it could be 1. So Q is in the integer interval 1 through 99. So returning back to here, we can make this very large by setting Q to 99, or very small by setting Q equal to 1. Either way, Q equals 1 or 99 maximizes R. So when we return to here, let's say we let Q equal to 1. We're saying one equivalence class has cardinality 1, and the other equivalence class has cardinality 99. So we've kind of shown this last part here that we have some sort of maximum sized relation if the relation admits equivalence classes of size 1 and 99 accordingly. The only thing that's left to do is like the first part, finding an R that provides these. So let's do that. So let's suppose that cardinality of x is equal to 1, so let's just say it has the value 1 in it, and then y is 99, so that'll just be the remaining values. This should be 100. So based off of this, we can kind of determine what R should look like. I mean, we said before, R is equal to the union of the cross products. So that's all we need to do. X cross X only contains one element, which is the ordered pair 1, 1. And then Y cross Y has a bunch of elements, right? It has 2, 2, 2, 3, 2, 100, 3, 2, 3, 3, 3, 100. All of these elements. And R is going to be the union, like all of this. And we've done it. We found our equivalence relation R. Now we don't need to even worry about like all of the other things from before, because that was handled in focusing on the two equivalence classes. So that's the first question. This one's kind of tricky, and there was a lot of algebra involved. But the one takeaway from this problem that you should remember is the truth that I wrote on the board about how equivalence classes partition the set that we're working with. Cool. 1 down, 2 to go. Okay, so here we have the second question. We can see the handwriting is starting to falter because my arm hurts from writing. But consider a set A with n greater than or equal to 1 elements. We color independently each of the elements of A red with probability 1/3 and blue with probability 2/3. Let R be the is the same color as relation on A. That is, if A is the same color as B, then the ordered pair A comma B is in R. And we're asked, is R an equivalence relation? If so, what are its equivalence classes? So How do we prove something is an equivalence relation? We've discussed this a couple of times throughout today's session, and we just need to show the three properties: reflexivity, symmetry, transitivity. So let's do that. So reflexivity is pretty simple, right? For all elements A in A, we know that A is the same color as itself, therefore it is related to itself. Therefore, we have reflexivity. So for symmetry, we want to show for all x and y in A, if x is related to y, then y is related to x. I won't really write this out because it takes time, but I'll just explain it in words. If we know x is related to y, then x is the same color as y. Well, that must mean that y is the same color as x, right? We're just sort of flipping it, but we still know that they're the same color. So symmetry also holds. Now for transitivity. So for transitivity, we're trying to show for all x, y, z in A, if we know x is related to y and y is related to z, then x is related to z. Once again, we can kind of explain this in words. If x is related to y, then x is the same color as y. And if y is the same color, or if y is related to z, then y is the same color as z. But we know that y is also the same color as x, so x is the same color as z. It was kind of explaining it in words, but yeah, it works. So all of these hold. That's a little bit hand wavy, but like, come on. How much more could you really explain? So yes, R is an equivalence relation. So now we just need to describe its equivalence classes. I mean, there's a couple of ways of doing this, but the way I like to do it is I know my equivalence classes must partition my set A. So why don't I just start with some element of A, figure out everything that belongs in that equivalence class, then look at the leftover elements, choose an element from there, determine its equivalence class, and so on and so forth. So we'll consider an arbitrary element of our set A. There's not much we can work with, except for the fact that we know it has some color. It's either blue or red. So without loss of generality, we'll just suppose that A is blue. Then what is the equivalence class with the representative A? This is going to be all elements of our set A, such that lowercase a is related to that element. Our relation is the same color as. We know A is blue. So everything that's in this equivalence class must also be blue, right? Because lowercase a is related to everything that's also blue. So in fact, this equivalence class is going to be all blue elements of A. So that's one equivalence class. We haven't fully partitioned our set A. We have to look at what's left over. But everything that's left over is red, because things are either blue or red. And you better bet that's our other equivalence class. So we have two equivalence classes, all of the blue elements of A, all of the red elements of A. You can verify that these are indeed equivalence classes. So that's part A. Let's move on to part B. So now we're asked to compute the expected value of the cardinality of R. Well, how is this going to work? We'll start from the fact that R is a subset of A cross A. So for every single possible pair in A cross A, it may or may not be in R. But when is a pair in R? For an arbitrary A comma B in A cross A, when is A comma B in R? Well, that occurs when A is the same color as B. Which means that A and B are both red, or they're both blue. So now we might start to think of like how we're going to compute this expected value. We'll look at every single pair in A cross A, and we'll assign it an indicator. And that indicator will tell us whether or not it's going to be in R. So we have an indicator for every single pair of elements, A and B, and we're going to see like what is the, I guess, the probability that that appears in R. What is the probability that these two elements are the same color? Let's start writing that out. So recall A is a set of some n greater than or equal to 1 element, so I'm just denoting it as this. and I have my indicators. X sub ij will be an indicator in a variable that is 1 when a sub I, a sub j is in R, when those two are related to one another. So now we can just express R in terms of these indicators and work from there. So we'll use LOE to say that the expectation of this cardinality is the sum of the expectation of our indicators, right? Every time we have a pair that appears in our relation, we're adding 1, the 1 from the indicator, to our cardinality. So we'll take the sum of all of them. And we're summing over all I and j. Instead of representing this as a single summation, I want to represent it as 2 summations, one for the i's, one for the j's. And the reason why I'm going to do that is I want to highlight what these subscripts could be, right? If we were to write out this summation, like not using summation formula, like this is what it's going to start to look like, right? x1 comma 1 plus x1 comma 2 plus dot dot dot. However, are all of these expectations going to be the same? x1 comma 3 is an indicator that is 1 if a sub 1 is related to a sub 3, which means we need to have both a sub 1 and a sub 3 being the same color. However, if we were to look at, say, x2 comma 2, that is going to be 1 if a sub 2 is related to a sub 2, meaning a sub 2 is the same color as itself. Well, that's always going to happen, right? If a sub 2 is blue, well, a sub 2 is the same color as a sub 2. They're both blue. Same thing, if a sub 2 is red, a sub 2 is still related to a sub 2. So this indicator is always going to be 1. And in fact, any time we have the subscripts being identical, or looking at the same element, that indicator will always be 1. Because we're only looking at one element. However, when the subscripts are different from one another, then we're looking at 2 separate elements. That's when we have to be a little bit more careful, because then they could be different colors. So let's rewrite this summation into some sort of familiar form. You'll see what I mean in just a moment. So we might remember seeing something like this from variance, where we separated the doubled terms xi sub I and all of the ones with different ones. We saw this a lot in variance, though slightly different. We just explained that this indicator will always be 1, so its expectation is 1. Now we just need to find the expectation of the other guy. So the expectation of an indicator is equal to the probability that the indicator is equal to 1. In this case, it's the probability that the ordered pair AI, AJ is in R. But what that means in words is that A sub I is the same color as A sub J. Well, there's 2 disjoint cases, one when they're both blue, one when they're both red. Since they're disjoint, we just add their probabilities. We'll use the fact that these elements are colored independently. So the probability A sub I is blue is 1/3. And the probability A sub j is blue is also 1/3. So the probability of their intersection is the product of the 2. And same thing here, except now the probability that they're red is 2/3. Summing these together, we get 5/9. So that's going to be the expectation over there. Okay, so let's just substitute and then solve it. This first term, we're summing the value 1 n times. So this is n times 1. And then we have to figure out how many unequal pair of elements are there, where both elements are not the same. You have n choices for the first one, anything from 1 to n, and n minus 1 choices for the second one, anything that's not the first guy. So the n times n minus 1 times 5/9. And you can simplify this, but I'm a little bit too lazy to do it, and it's also kind of early in the morning, like 1 a.m. So we'll leave it in that form. There you go. That's the answer. So yeah, that's the second problem. Let's move on to the last problem. I don't want to get kicked out. Okay, this question is going to be a doozy. I will do my best to explain this in a way that makes sense, though no promises are guaranteed. If you have any questions, ask your TAs or come to concept office hours. We'll discuss it in way more depth. I suggested this question for recitation, and then I started to regret it because it's a bit complex. So let G be a bipartite graph with the cardinality of V equals to n. Suppose each vertex has a list of size at least log base 2 of n possible colors that it can be. Show that it is possible to provide a valid coloring of G such that the color for each vertex comes from its list. This is a very crazy question to parse. We have a bipartite graph. Something that more or less looks like that. We know that the cardinality of the vertex set equals n. But also, for each vertex, we can take a look at it. Each vertex is going to have its own list of possible colors that it can be. For example, this one could be red or purple or some other amount. But there's at least log base 2 of n of them. We want to show that it's possible that for each vertex, we can choose some color on its list. And do that for all of the vertices, such that the resulting coloring is valid. That is, no two edges, or no edge has two endpoints that have the same color. You might think that this is very easy. You might start out small and let n equal 4, and then each vertex has two colors, like red or blue, and then sort of just work through it and be like, oh, okay, this kind of makes sense. And the reason why it's 2 is because log base 2 of 4 is equal to 2. However, you'll quickly realize that this is kind of challenging. And the reason for that is because we don't really know what these list of colors look like. Right? If I look at two vertices and look at their lists, the lists could be identical to one another, meaning that they have the exact same possible colors, or they could be vastly different from one another. On top of that, log base 2 of n is actually a very small number. For example, when n is equal to 1000, log base 2 of n is approximately equal to 10. So if we have 1,000 vertices in our graph, each vertex will have at a minimum of 10 colors that it could be. All of them could just have 10 possible colors, and you have very few options. So that's when things will get a lot more tricky. So this is one of those cases where we want to show that something is possible, that a coloring exists. But to just provide it outright would be very, very challenging because we don't have many tangible things to work with. As such, we decide to use the probabilistic method. How might you start to logic about this? I might start to think that whatever colors I provide to the left-hand side, all of these vertices could be the same color, since there's no edge between any two vertices on the left-hand side. And similarly, all of these vertices could be the same color. We don't need to worry about any interference of coloring there. What this means is if I have some collection of colors, let's say I have some collection of colors, red, blue, and orange, and I'm saying these colors are reserved only for V1, which is my left-hand side. Meaning, whatever, I can color these whatever I want, but those colors must appear in my overall big grouping of colors for V1. These colors are reserved for these vertices only. And say I have another completely disjoint grouping of colors for V2, meaning I can color these whatever I want so long as these colors only come from V2. As long as these lists are disjoint, then my coloring will be valid, right? There will never be any interference because an edge goes from a color on this side to a color on that side. We've guaranteed disjointness. So that might be a goal we want to have. Construct these two disjoint lists. However, there's something to keep in mind. we can only color these vertices in V1 with one of these colors if we can find a color in my reserved set that appears on the vertex's personal list. So in this case, I found red on its list. Red is one of my reserved colors, so I can color this one red. But if this guy doesn't have red, blue, or orange on its list, then I'm in a bit of trouble. So that's another thing to keep in mind. So why don't we do this? Let's take a look at each vertex's personal list and conglomerate all of the colors together. So we'll let X be the set of all colors over all of the lists. Note, it's not a multi-set, so we don't really care about repetitions. We just want to see every color that a vertex could be colored. And what we'll do is we'll try to construct these lists. We'll look at a color, and we will assign it to one of these lists. For each color, we will either put it in V1, V2. It'll occur with equal probability, right? So I look at this color, purple, and maybe I'll flip a fair coin, and if it lands on heads, I'll put it in V1, otherwise I'll put it in V2. So as we said before, the vertices in V1 can only be colored using our reserved list for V1, which we've just probabilistically determined with our procedure above, and the same thing for V2. So now we basically want to analyze, did we do a good? Does that give us a coloring all the time? And if not, what's the probability of failure? So what is the probability we fail? What is the probability of not having a valid coloring? This would only occur if a vertex, its personal list of colors, say we look at a vertex in V1, we will not have a valid coloring if none of its colors appear in the reserved set for V1. So let's take a look at how many vertices that fall into this condition. What is the expected number of vertices that we will have such that no color on their personal list is in the reserved set? So we define some random variables. N is going to count the total number of failed vertices, or the amount of vertices where no color on the personal list is on the reserved set. And we'll have an indicator for each vertex. So by LOE, we'll just take the sum of the expectation of the indicators. So the expectation of our indicator is equal to the probability the indicator equals 1, which means none of its personal list colors are on the reserved set. So that means color 1 is not on the reserved set, intersected with the case where color 2 is not on the reserved set, et cetera, for every single color that is on the list. We know that there's at least log base 2 of n of them. Well, the probability that color 1 is not on the reserved list, well, for each color it was either in the reserved list with probability 1/2 or not in the reserved list with probability 1/2. For clarity, we had 2 reserved lists. We're looking at the probability an indicator is equal to 1. This I is for some vertex Vi. And this belongs to either V1 or V2. So Vi has a known reserved set. We just need to know whether or not color 1 is in that particular reserved set. So say we know Vi is on the left-hand side, V1. Then this is basically saying the probability that color 1 appeared in the V2 reserved set. So I probably should have been a bit more clear, but whatever. So yeah, that probability for the first color is 1/2, and same for the second color, and so on and so forth. And we multiply this, we multiply this the amount of times that there are colors in this personal list. But this product is going to be at most 1/2 to the log base 2 of n, right? Because We can stop here if there were exactly log base 2 of n colors, but there could be more, which only just decreases the value of this product because we're multiplying by something smaller than 1. So it's going to be less than or equal to that. And this entire expression is 1 over n. I just realized I kind of wrote the problem a little bit wrong. I don't feel like re-recording all of it since it's a small mistake. This should not be greater than or equal to, this should just be greater than. And that changes this slightly because this less than or equal to just becomes a less than sign. So we know now that the expectation of n sub I is less than 1 over n. So now we can return to here. This is going to be less than the sum from I equals 1 to n of 1 over n. We're summing this n times, which is 1. Therefore, we have concluded that the expected value of n is less than 1. And we're done. The end. No, of course, I'm going to explain to you why we're done. N denotes the number of failed vertices, right? We were curious as like, when are we failing? Like, how badly are we failing? And if we were to count the total number of failed vertices in expectation, based off of like all of the possible ways we could have done this coloring, or these assignment of colors to these reserved sets, in expectation, we're failing for less than 1 vertex. It could be like 0.99 vertices or whatever, but it's less than 1. Why is this so important? N takes on integer values. Whoa. Right? When we count the number of failed vertices, it'll never be 1.5 failed vertices. It'll either be like 1 or 2 failed vertices. Since this is less than 1, we must have an occurrence where n is an integer value less than 1. That's the only reason why this expectation would have been dragged down below 1. You can prove by contradiction that if n was always 1 or larger, then we would never have an expectation less than 1. Therefore, there exists an assignment of whatever, blah, 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 such that n equals 0, which means there will be a situation in which we fail on no vertices. Therefore, a coloring is provided. I'm not super pleased with this explanation because I feel like I didn't give you enough intuition as to how to approach this type of problem. If you want to discuss that, feel free to ask your TAs about it or come see me in some sort of office hours and we can discuss it a little bit further. But I hope I was able to somehow construct a journey for you in how you would go about doing probabilistic method problems, realizing that a direct approach isn't necessarily going to work out, but then how you would go about constructing your random procedure. If we look back at the whiteboard, let me do that real quickly. Step 1 is garbage. Construct a random procedure to generate candidates for X. That's not easy to do. What does that mean? Generate a random procedure. How do you even think about that? I hope what I've just shown you now starts to get you in the right mindset of how you might construct a random procedure. Here we took quite a bit of time to finally get to the point where we were assigning these colors to these reserved sets with some sort of probability. That was my randomized procedure. It took a while to get there, but that's what we're trying to build up to. I really, really hope that helped. That's it. That's all I can give to you. Hopefully this recitation was helpful. I know there was a lot of content. I don't know how long this recitation will be because I haven't edited it yet, but if you stuck with it the entire way, kudos to you. Very, very happy to hear that, and I truly hope that this helped. Anyways, have a good day, night, whatever time of day it is. I need to sleep.